подготовка у наших студентов, участников разная, различная, и специальности разные. И мы никогда не знаем, кто будет участником нашей школы. Это накладывает определенный отпечаток на специфику работы над проектом.
So the students represent various specializations and various degrees of expertise. So we never know who's going to participate in the school prior to the selection to the school. So that creates a certain specifics in this kind of project.
Конечно, в предыдущие годы все такие неувязки и то, что мы представляем разные языковые среды, разную образовательную платформу, разные подходы в образовании, и соединяем этих студентов в одном проекте, все неувязки, они всегда компенсировались общением личным, через культурную программу, через общение, которое каждый день было у ребят. Это очень был положительный момент в понимании друг друга, когда они работали вместе над проектом. В этом году такой привилегии не было. Мы были разъединены территориально.
And previously, all those discrepancies, I mean, different languages, different levels of education, different expertise, they were mitigated by the ability to communicate directly face-to-face, getting together here in Moscow during the program. But this time we were separated and we worked from our respective countries and homes and classes. So that's what made this project special.
Но, как говорится, у нас, у русских, есть такая поговорка: не было бы счастья, да несчастье помогло. Может быть, это нам специально дано такое обстоятельство, чтобы получить бесценный опыт виртуального общения.
So we've got a Russian saying, it wasn't for the fortune, but the misfortune helped you. And this is what happened due to the peculiarity of the situation. We gained some kind of valuable experience on how to work remotely under those circumstances.
Но что получилось, мы увидим сегодня. Сейчас я передаю слово научному руководителю проекта, доценту университета имени Баумана, который руководит проектами уже более 10 лет в этой школе, Владимиру Александровичу Игрицкому.
And we are about to see what kind of results we achieved team project-wise. So I'm handing it over to Vladimir Igritsky, Bauman Moscow State Technical University Associate Professor, who's been leading team projects over in those schools for 10 years.
А затем студенты, каждая группа целевая, представит результаты своей работы, и мы сможем задать им вопросы.
So then the students who worked on different groups will present the results of their activities and we'll be able to ask them questions.
Володя, пожалуйста.
Здравствуйте,
господа.
Hello, ladies and gentlemen.
К сожалению, сегодня у меня технические трудности с видеокамерой, поэтому я покажу только презентацию, а не свое лицо.
So unfortunately today I'm experiencing some kind of technical difficulties with my camera, so I'm about to show my presentation, but not my face.
В начале школы студентам было, нашим участникам было задано задание на их коллективный научно-технический проект. Вот, и в этот раз он был посвящен освоению Луны.
So the students were tasked with a certain task in the beginning of the team project, and this particular project was devoted to the development of the moon.
Вот. Но само собой, что за 2 недели мы не можем научить людей тому, чему учат многие годы в университете, поэтому Здесь главное, чего они должны научиться, это работать вот в интернациональном проекте, применять некоторые экспертные методы, ну а также изучить некоторые особенности именно космической техники.
And of course, it's kind of impossible to give students all the knowledge which are given to people in the university over 6 years within 2 weeks. So the tasks pursued here are to give the opportunity to the students to work and solve the problems within an international group, use some expert methods, and get familiarized with some peculiarities of the space technology.
Так, ну, сейчас, как известно, в России, Китае и США проводятся работы по созданию новых сверхтяжелых ракет для освоения Луны.
So as we know, China, Russia, and US are developing their own super heavy launch vehicles for the lunar missions.
Вот. Однако все еще остается актуальный вопрос. Все ж таки, что мы будем делать дальше, после того, как просто полетим туда, повторяя путь экспедиции Аполлона.
However, it's still a standing question. What do we do on the moon after we just come here, similarly to Apollo landing on the moon?
Ну, на мой взгляд, очевидно, что нужно строить какую-то инфраструктуру на месте.
But to my mind, it is kind of obvious that it is necessary to establish some kind of infrastructure in place.
Но сейчас все-таки у нас не 60-е, 70-е годы, вот, и поэтому, наверное, отправлять туда людей, чтобы они это строили, ну, не обязательно.
However, we have progressed quite a bit since 1960s and 1970s, so it's not really necessary to send people there to establish that infrastructure.
Вот. Сейчас это можно сделать с помощью специальной робототехники.
So it can be done by means of special robotics these days.
Однако, по факту, эта робототехника все равно нуждается в надзоре со стороны людей.
So, however, those robots require some supervision by people, by humans.
Да, ну, такой подход был использован еще при работе первых планетоходов, луноходов в 70-х годах.
So this kind of approach was used during the first rover missions in 1970s.
Однако, все-таки расстояние от Земли до Луны не позволяет сделать такое дистанционное управление комфортным, поскольку образуется довольно-таки заметная задержка.
So, however, the radio delay between the Earth and the Moon doesn't make it possible to use the direct remote control.
Ну, поэтому есть предложение рассмотреть вопрос, что мы рассмотреть такой вариант, что у нас космонавты и астронавты находятся вот непосредственно на Луне и оттуда с помощью специальной спутниковой группировки управляют всем процессом исследования и освоения Луны.
So this is why the concept we pursued in this project is having a group of cosmonauts and astronauts at a certain base on the Moon and controlling all the process of lunar development and via using a constellation of satellites around the Moon.
Ну, соответственно, вот это вот облако спутников, оно должно предоставлять и связь, и дистанционное зондирование, и навигацию, и так далее.
So that constellation should provide the capability of communications, navigation, positioning, etc.
Вот. Но здесь я обратил внимание на радиационную опасность как ключевую в вопросе пилотируемых полетов в космос.
So when I was setting the task for the students, I paid some attention, quite a lot of attention to the problem of radiation hazards being one of the key problems of the human spaceflight.
Вот. Ну и, соответственно, все-таки, что касается самой лунной базы, то ее по традиции предполагалось заглублять, предлагается, да.
So, and as for the lunar base itself, it was proposed in a kind of traditional way to put it under the lunar surface.
Вот, соответственно, тема была обозначена вот таким вот образом, как тут написано.
So this was the topic or the task for the seed project.
Вот, то есть создать всеобъемлющую систему для вот, освоения Луны на основе соответствующей базы.
So basically to develop a comprehensive lunar exploration and development system using the lunar base.
Вот, хочу обратить внимание, что само собой это делалось для самых ранних этапов проектирования, поскольку время очень ограничено. Но здесь вот по российской классификации этапов работ мы шли. Соответственно, их задача состояла в том, чтобы основные концепции разработать и подтвердить их основными же расчетами.
So, and we got down to the design and we followed, in Russian terminology, those stages of the project development. So we decided to stay at the stage of the technical proposal, which would be generating the concept of the base.
Вот, соответственно, были предложены следующие задачи для решения этой проблемы. Это, собственно, разработка транспортной системы для перевозки экипажа и этих туристов, может быть, тоже. Вот, лунной базы с роботами разворачиваемой. Собственно, эти самые роботы, спутниковую систему и все, что еще понадобится.
So, therefore, the specification, the requirements for the project were as follows: to design the transportation system, to design a lunar base which can be deployed robotically, to design robots, that very robots which will be deploying the base, satellite system for navigation, telecommunications, etc., and to design some other equipment in need for this kind of project.
Вот. Ну, в качестве дополнительных требований выдвигалось, соответственно, радиационная защита реголитом, использование воды для производства компонентов топлива и дополнительно в качестве варианта я им предложил рассмотреть такой случай, когда мы, чтобы уменьшить количество операций стыковок и всяких там проблем, которые могут быть с этим связаны, кабину с экипажем переносить непосредственно прямо от МКС к дверям этой, собственно, базы, без необходимости их перехода в какие-то другие объемы.
So, in addition, I asked students to work on the use of the lunar regolith for the radiation protection of the base, using water as a source of propellant, and I also suggested them to move the crew module directly to the lunar surface from the ISS.
Да. Ну и далее большая наша команда студентов была поделена на группы, вот, в соответствии с направлениями работы здесь перечисленными. Вот, соответственно, сама база, кабина, универсальная посадочная платформа, баллистика и робототехника.
So the students were split into 5 groups dealing with the specific problems outlined on this chart.
Вот, ну и, соответственно, на этом было было пожелание им хорошо сработать. И я хочу сказать то, что они проделали очень большую работу. Я им благодарен. И несмотря на то, что вот в этом режиме дистанционного проведения конференции получилось так, что они были почти оторваны вот от своих научных консультантов, я считаю, что им удалось достойно показать, что они могут сделать даже вот за несколько вечеров.
But at this point, I wish success with their project, and just like to precede the event, I would like to say that to my mind everything worked fine, and under the condition of being separated from their science consultants, the students performed very well.
Вот. Спасибо большое.
Thank you very much.
Представляю вашему вниманию доклад наших студентов по результатам, участников по результатам их работы.
Giving the floor to the student participants to present the results of their activities.
Володя, спасибо большое. И прежде чем ребята начнут докладывать свои результаты, разрешите мне представить членов нашего жюри, огласить этот список членов
Vladimir,
нашего жюри.
thank you very much. Thank you very much for the presentation. And before we get down to the students' reports, I would like to introduce the members of the panel today.
У нас сегодня будут участвовать в обсуждении проекта, в оценке проекта представитель ректората университета, представитель руководства университета, доцент кафедры баллистики и аэродинамики Александр Юрьевич Луценко.
Bauman Moscow State Technical University administration will be represented by Associate Professor of Ballistics and Aerodynamics Department Alexander Lutsenko. He's also a Deputy Head of Research and Educational Complex.
Летчик-космонавт России, выпускник МГТУ имени Баумана, наш большой друг Молодежного космического центра Олег Иванович Скрипочка.
A great friend of Bauman Moscow State Technical University Youth Space Center, cosmonaut of Russian Federation, Bauman Moscow State Technical University graduate, Олег Иванович.
Приветствуем.
Да, добрый день.
Добрый день.
Yeah.
Пообщаемся еще сегодня не один раз. Также в жюри у нас присутствует выпускник МГТУ имени Баумана, кафедра космические аппараты и ракеты-носители, ныне главный специалист, работает на предприятии Арсений Павлов.
So we have also got Arsenij Pavlov, who is a Bauman graduate of the Department of Launch Vehicles and Spacecraft. He's currently working for the industry.
Hello, dear colleagues.
На месте, Арсений?
Yes, I'm here. Я здесь. Видно меня, слышно?
Arsenij Pavlov.
Есть звук.
Спасибо большое. Мы отследим вас. Отследим. Вот, теперь видим. Студенты должны видеть. Спасибо большое. Также у нас в жюри сегодня доцент кафедры баллистика и аэродинамика, наш сотрудник, руководитель учебно-научного центра приема и обработки информации и Центра управления полетами малых космических аппаратов МГТУ имени Баумана Гришко Дмитрий.
So we've also got the Bauman Moscow State Technical University Associate Professor, the head of
только теоретической механики, а не баллистики.
Yes, so Dmitry Grishko, who is an Associate Professor of the Theoretical Mechanics Department of Bauman, and who is heading a laboratory for the satellite control and remote data acquisition.
У нас сегодня очень ответственный момент, потому что среди наших гостей которые тоже могут являться членами жюри и задавать вопросы, и оценивать проект. Наши коллеги, друзья, партнеры, гости, мистер Джордж Эбби.
So it's a critical and responsible moment, and we've got some friends, partners, and colleagues here, in particular, Mr. George Ebbie,
которого мы с удовольствием слушали лекцию. Это директор программы обмена между нашими университетами, университет Райса и вообще американскими университетами со стороны Соединенных Штатов Америки, и нашей программы директор, который 10 лет возглавляет эту программу с американской стороны.
So, and besides of all the other accomplishments, Mr. Reddy gave us a wonderful lecture. We were delighted to listen over the course of his science school. Also, Mr. Reddy has been leading the exchange program between a number of the U.S. universities and Belmont University for 10 years.
Также Ольга Константиновна Банова, директор Центра космической архитектуры города Хьюстона, университета Хьюстона и города Хьюстона, которая также 10 лет участвует в этой программе в качестве соруководителя.
So we've got Professor Olga Banova of University of Houston, who is leading a Center for Space Architecture, and she's been a co-director of this program for 10 years.
И второй соруководитель, который также 10 лет участвует в этой программе, Джейсон Лайнс, который работает в университете Райса.
So we also got Jason Lyons of Rice University, who's been co-director of this exchange for 10 years as well.
И сегодня у нас специальные гости. Мы очень рады этому и горды, что сегодня ребят будут слушать астронавты НАСА, Билл Шепард, который совершил 4 полета в космос, 3 из них на различных типах шаттлов. Это были и Endeavour, Atlantis, Discovery и Columbia. И 4-й полет был на Союз ТМ-31, это человек, который был командиром экспедиции, первой экспедиции на Международную космическую станцию.
So we are also honored to have NASA astronauts on the panel. We've got Bill Shepard, who flew 4 missions on 3 different space shuttles, Soyuz TM-31 and the International Space Station, and Mr. Shepard has been a commander of the first International Space Station.
Вот несколько часов назад наш космонавт Сергей Крикалев, который, к сожалению, по техническим причинам не может, физически не может сегодня подключиться, он в дороге, он сказал, какой шанс был пообщаться с моим коллегой, другом, партнером, но мы пообщаемся еще.
So initially we were expecting Sergei Krikalev to join us today, but he physically can't do it because he's on the road right now. But he said that he had a great chance to talk to his friend, colleague, and partner. But we are unable to do it right now, and we'll probably do it later.
И также наш специальный гость сегодня – это астронавт Джим Адамсон, который совершил 2 космических полета, и сегодня он с нами.
So, and another astronaut on the panel is Jim Adamson, who flew 2 missions and who is with us now.
Ну что же, теперь слово студентам, пожалуйста.
So I'm giving the floor to the students. The floor is yours.
Welcome everybody. We're starting with base team.
Ребята, пожалуйста, я только одно прошу. Представляйтесь, пожалуйста. И еще я хочу, пока мы не ушли далеко, у нас в жюри еще должен один член жюри быть. Я его не увидела, но, может быть, он подсоединился. Это Анатолий Копик, директор по маркетингу. Это частная космонавтика, предприятие «Спутникс», фирма «Спутникс». Анатолий здесь? Отлично.
I would like to ask the students to introduce themselves before they speak, and on the panel, I would like to say that we've also got Anatoly Kopik, who is the marketing director of Sputnik's company, which is a Russian company in the private space sector.
Спасибо.
Всем привет.
Да, спасибо.
Hello,
Все,
everyone.
начинаем.
I'm Michael Denisov. I'm from the BMSTU, Bauman Moscow State Technical University, and today me and my team are going to propose you the concept of a lunar base. So, as you can see, we have a lot of people all over the world, and it is quite fascinating, even though we are online this year. So here you can see our team composition. So we've divided into some teams and worked each on a separate subject. First things first, we have to consider the location of a base. For our design location, we chose the South Pole because of a comfortable temperature regime and the availability of water in the regolith, so we can extract it easier. Our goal was to propose a multi-purpose environment for the future astronauts to settle in, to make it spacious and also extensible, and also account for some safety, nevertheless. So we're separated our base deployment plan into some stages, and into 3 stages to be exact. And here you can see some plans of the desired location. So first things first, we have to deliver some basic blocks and equipment, assemble the first energy source, and we will try to make things a little bit clearer later as we go on. So we have to deploy our first module, and all the system is going to be modular to make the overall deployment easier. So at the second stage, we expand our lunar base further. We raise our safety in terms of energy, so we install more reactor assemblies. We ship the greenhouse and install it, and we try to make our base as self-sufficient as it can get. During this stage, we have some problem with resource mining, because we still don't have enough power, we still don't have enough robotics, we still don't have the needed infrastructure, for example, the robotics team will propose you later, and so on. So at the third stage, we complete the main part of the lunar base, and we can settle for the further expansion. So this is basic module showcase. There you can see a living quarters final assembly and the results of a finite element analysis for an inflatable pod that was proposed during the design stage. Also, there you can see some specifications of a proposed base. So dimensions, mass requirements for the lander, and overall math of the complex. And as you can see, it's quite spacious for the crew of 24, so it can house some living quarters, some machinery, and some special equipment, for example, life support equipment and something like this. The separate showcase is going for the foldable bridge between the pods, because we try to make it as spatial as possible, but also account for an easy deployment. So it incorporates extensible bellows or a foldable frame with inflatable shell that help us to provide the very good ceiling enclosure and also a relatively low mass compared to the all the rigid systems. Nevertheless, to make our habitats safe from the outside environment, we need to consider some problems such as radiation protection.
Yes, the first radiation shielding thickness evaluation was obviously referring to primary particle radiation. As you can see from the graphs, a good primary shielding resulted in a 50-75 centimeters thick regolith layer. However, the secondary particle dose increases approximately by 47% in presence of 100 grams by square centimeter regolith layer, which corresponds more or less to 65 centimeters in thickness. Considering the linear slow decrease of the effective dose values caused by secondary particles, for example, a 50% reduction in transmission can only be obtained with a more than 200 grams by square centimeters layer, a possible solution could result in using a 5-6 meters regolith shielding. Of course, this is a conservative approach to take into consideration possible fluctuations in density. Said so, the possibility of additive manufacturing buildings that we considered in first instance has to be discarded both for payload and for time reason. The only reliable alternative will be then covering the inflatable we were talking about before, which have obviously to be airtight, with a layer of 6, as I said, 6 meters thick regolith. Due to low gravity of the moon, the regolith will be the weight of the regolith will be partially counterbalanced by the inflatables inner pressure.
Dealing with the regolith problem, we've got some problems remaining with the autonomy of the base. We still have to replenish our oxygen levels. We still have to replenish our food levels somehow. So that's where our life support sub-team has something to offer.
All right, hi, I'm Amanda Body from Rice University, or alumni of Rice University. So I looked at the food production. I assumed a daily diet of about 2,200 calories per person per day. And I assumed about 24 people per year. So the sources of the macro or the micronutrients I chose were rice, silkworm, and sunflower. And I chose those specifically because they were the most nutrient dense per unit of area. And on this table, you can see the breakdown of the percentage of the daily diet, the space requirements for each, the water requirements, the power requirements, and the oxygen generation.
So after making this table up, we've decided to use the results of this table and produce a concept for modular greenhouses that can support our crew members' needs in food and oxygen, partially at least. So we've proposed some of inflatable two-story dome structures that use a soilless method of raising plants, called aeroponics, to provide the needed water and nutrients for the growth of plants, and both lower the level of water and nutrients that needs to be injected into plants, so thus raising the return of investment level from those greenhouses. Our other side of the life support was some medical side of life support. And
Hi, I'm Kelly Graham, and I'm from the University of Houston. My friend Harry is also from the University of Houston. He was supposed to go over the greenhouses, but he couldn't today, so thank you for doing that for him. However, the medical side that we were looking at, there are several machines to maintain human health while on the base, according to the ones being used on the International Space Station right now. They would need to be modified because of the partial gravity, but that would be a simple adjustment with weights. Another really important consideration is because having the tourists and a crew of 24, there's going to be a lot of EVAs. The most crucial aspect of staying safe on the moon is performing EVAs no more than twice a week to limit exhaustion by the crew, and having 2 flight surgeons on base at all times to make sure that human health is always taken care of. And additionally, not doing EVAs in craters where the slope of the crater is between 20 to 26%, because current spacesuit designs, in addition to the friction of the soil between the boots and, is not conducive for having the slope of those craters, and past crews have found that that's can be a dangerous element. So we want to limit doing EVAs in those types of craters, and also limiting that will limit radiation exposure to further protect the crew.
Thank you very much for your information, Kelly. As you can see, just being on the moon implies some implies certain restrictions for our team, and to be very. Sorry.
I'm Yana. I'm a BMST student. In the picture, there is a concept of our reactor. For power generation at our base, we chose nuclear reactor because it's a constantly operative source, which is potential for long power producing. Another advantages are its tolerance to moon dust, and it's also easy to supply and easy to maintain. And the problem of produced radiation was solved by sufficient radiation shielding. So such structure is rather simple, safe, and was well tested for years. We think it's the most attractive choice for energy source.
Okay, so it's not always enough just to produce energy. Sometimes you need to store it for the spike moments in our energy consumption. That's how our proposed storage method comes into play. So
okay. Okay, we choose to store energy as heat in regolith, which is easily found on the moon. And like this, we don't need to bring from Earth heavy batteries. The energy will be transferred from the reactor to the regolith with pipes who contain helium, which is the heat transfer fluid. Helium seems a good choice because its solidification temperature is very low. Like this, we have the heat source for a Stirling engine. The heat sink is the regolith and moon's ambient temperature. And with to prevent the losses of heat in regolith, because the losses is by radiation, we place a reflector all around the regolith. And with this system, with the Stirling engine and the standard electric generator, we can provide at maximum 85 kilowatt in 1 cubic meter of regolith. Okay.
Going out from the energy production, we need also to consider some resource issues that arise inevitably during the deployment phase. So we need resources. We need to fuel our landers. We need to supply oxygen to our crew members. We need water for our greenhouses, and we need a lot of resources. So we try to use a regolith to make some resources out of it at the later stages.
Hello, my name is Anna Yakovleva. I'm from Moscow State Technical University, and you can see how many resources we need. and there is about from 3 to 7% of water in regolith, so we will extract water from them. And for my calculations, I use as an average 5%. And the water extraction process begins by drilling the soil and carrying them to the station for heating, but we can get the water only on Moon only by heating because of pressure. It's too low on the Moon, and with this pressure, the ice hidden in the regolith will immediately sublimate. So we need to use a compressor to raise the pressure and get the water. Part of water will be given for splitting into hydrogen and oxygen for the fuel for our spacecrafts. And this process will do it by electrolysis. And after calculations for each of points, I got total numbers on the next slide, please. Oh, this is total numbers. And we can see proposed water extraction scheme.
Well, and this is I'm Jorge, a Mexican student of BMSTU, and this is the proposed water extraction scheme. We basically will dig in the Shackleton crater and deliver the regolith dig to the industrial heater that was mentioned before, which has also a compressor. Once we get the water in the form, we will put it in large deposit, which from there we will take it to the road base. And this process will last 24 hours. Well, 21 of them is going to be for actual working and getting the regolith in water. And 3 hours are going to be for technical maintenance of the whole system not to crash. So in total, we will be producing an average of 21 tons. And well, that's basically everything of the lunar base. Thank you.
Okay, thank you for your attention. And now we'll switch into the robotics team, if I remember correctly.
Good evening. It's evening in Moscow. I mean, it's 6 p.m. in Moscow. My name is Jan. I'm from Bauman University. And today, my colleague Ismail and I are going to present the results of robotic team work. So first of all, we try to identify which task should robot perform at the lunar base. So the main aims of lunar robotic system is a solution of transport problems, first of all, then base maintenance and resource collection, and how to carry these resources. So we decided to use the following types of robots perform these tasks. So for the first time during the first missions, we need a cargo heavy robot that can build the station and can transport heavy new models of the base, and also a crew landing model from the landing site to the place where lunar base is situated. When the base will ready to for long missions, we need a multi-agency system of robots that can extract resources and water from the lunar regolith, hold scientific expeditions, and support the base work. And in the far future, as you see, of course, we will need a transport system to deliver cargo between different parts of the base. And what about navigation, Ismail? You're welcome.
We need a system of navigation on the moon. And so an idea is to use our system from aviation, which with it is possible to determine the position of the rover relatively to a landmark system, for example. And with this system, you can also determine the direction and the distance to go to the station. We can also combine this system with another system who sends information on the basis resource available on the station. The main advantage of this system is you can It is very robust and simple to conceive, but it has only an optical range of about 2.5 kilometers in theory on the moon. Can you switch the diapo?
Yep.
Thank you. We can describe systems electric of a rover like this. On the right, you have a real-time loop with and the state of the rover. And on the left, you have the interface with the rover. It is possible to use a remote command to send a command to the rover. And it can also perform automatical tasks on the command of other rover. Can you show the next slide, please? So the rover will have two main sensors. It will have a cameras system with a vision camera and thermal camera to have a peripheral vision of environments. It will also have attitude sensors to check the state of the rover. The rover will be powered with solar panel and battery, and an energy power system will manage the energy of the rover and power the brushless motors. And the communication system will allow to send the command to the rover and communicate its states and the resources available. Can you show the next slide, please?
Yeah, and now I'd like to tell you in short about the concept of our rovers. The first rover is a cargo rover, which used for mostly for transport as a transport system. It consists of a lifting platform that can be raised by the manipulator, and two manipulators with 7 degrees of freedom that can solve different problems, different kind of problems. For example, on the slide you can see how this cargo rover unloads the crew landing module and transport it to the base. Some technical details of this cargo robot you can see on the slide. So the second robot is a small rover, so female.
So the idea is also to make a little small rover to perform two main use. It is to carry passengers with their equipment, or to carry and extract resources autonomously. So the idea is to have a standard platform on which you can plug two modules, a resource collecting module or a passenger module. And on the top, you can see the different specifications of this little platform. They are based on the Apollo's rover, and it will be a little bigger than the Apollo's rover.
Okay, and in the conclusion of our presentation, I'd like to say that there are a lot of tasks that robots should perform on the surface of the moon, and of course we can't perform all these tasks only by robots. That's why we need some kind of a transport system for the moon to deliver some cargo from one point on of lunar base to another. And in our mind, the cableway is the best solution for the moon to solve these transport problems. So that's it for robotics, and I'd like to introduce the landing platform group. Thank you.
So good evening, morning, and afternoon, ladies and gentlemen. I'm Maxim Lysenko, BMC2. Alex Kolchin and I are the leaders of the remarkable people. We are happy to present you the concept of for moon landing platform we have come up with during our time in SDTP 2020. The main purpose for our craft is to deliver 7-ton heavy crew cabin or similar amount of cargo to the lunar surface, starting from ISS. Allow us to present some technical solution we have come up with to make sure that our landing platform can achieve that goal. Here you can see what task our team members have been working on.
Hello everyone, my name is Alex and I'm from BMSTU. So our development of landing platform had a lot of designs and changes. In the first variant we had vertical position, but due to that crew model have shield protection on one side, we can connect pair. Also the height, it was around 8 meters, was too much and it would be difficult for robotics team to take crew model from there. That's why the layout of crew capsule should be horizontal. In the next version, we tried to make our platform as low as we can, but we had problems with dimensions and layouts of fuel tanks. When we tried to divide the oxidizer tanks into small ones and put them around of our center fuel tank. Also in this design we had 4 engines, but that increased the mass and decreased the reliability. After that, we tried different designs and then we went back to our first design. So we made the same layout of the tanks and changed the connection with the crew model. We made it horizontal. The next slide, yeah. So as you can see here, it's our final design. Here we optimized its mass and also made suitable height, which fits into requirement of robotics team for crew cabin disconnection. From the bottom, you can see landing lengths, which are connected to strong frames. We have forward tank with oxygen as oxidizer on the bottom and fuel tank with hydrogen on the top. Between these tanks, we have service model with engine system inside. Also, we have RCS systems on the frames. On very top, there is a frame with attachment system for crew model. The total mass of our landing platform is 32.8 tons. Dry mass is 3.5 tons. The total height is 6.6 meters and the width is 5.7 meters. We can carry 7 tons of cargo and our platform can be carried to the orbit by Falcon Heavy rockets.
Hello, my name is Fedor from Bauman University. We have chosen hydrogen as our fuel due to it being widespread on the moon, and liquid oxygen as our oxidizer, as it was mentioned before. Our engine is based on the Centaurus booster engine, which utilizes these components of fuel. Similar to the Space Shuttle main engine, we will be able to provide the maintenance for the engine on both Moon and the ISS, and we will also be able to replace the engine in case of a failure. The chosen liquid fuel oxidizer pair is rather promising due to its high specific impulse. However, the cryogenic nature of these fuel components makes the structure of fuel tanks complicated. It was suggested that the helium tanks that are used for tank pressurization should be stored inside the hydrogen tank. Such a system was implemented in the Saturn V rocket. This decision, in theory, should lead to the decreasing the volume of inflation tanks and thinning their shell. For delivering 7 tons of cargo, we will utilize refueling operations on both the Moon and the ISS. In order to provide refueling capability on the lunar surface, hydrogen-oxygen fuel pair was selected, as it was already mentioned before. Cryogenic fuel pair pose specific challenges. Nevertheless, fuel tank's temperature is kept only using passive thermal control system, variable density multi-layer thermal insulator. This protection will keep mass losses of hydrogen per day at about 2%. To achieve such a small loss, 25 layers of metallic foil are required. Fuel for photon fuel cell is included in main tank volumes. Amount of hydrogen required for continuous photon operation is equal to 77.3 kilograms. In order to drain the fuel tank from continuously in microgravity, capillary fuel intake is used. The hydrogen fuel tank is pressure stabilized and suspended in external frame. The loads from cargo are passed through external support frame. Material of choice for both fuel tank is an aluminum lithium alloy Li2195. During nominal main engine operation, hydrogen tank is pressurized using heated hydrogen gas siphoned from engine's cooling system. When the main engine is not in operation, a preheated hydrogen gas is used to keep the nominal pressure inside the tank. Next slide, please.
Hello, my colleague Dimitri from University of Southern California and I, Sarfaraj from Seoul National University, South Korea, we both work on the engine. So for the central sensor system, we divided into 3 parts, as you can see, the solar sensor, the stellar sensor, and the landing sensor. For the solar sensor, the orientation determination and stabilization system has been determined, and we can see all the figures in the right side in the first white background. And the instrument is intended to provide a spacecraft control system with data on 2 angular coordinates of the direction to the center of the sun in a coordinate system defined relative to the instrument mounting surface. And for the stellar sensor, which is built as 2 separate assemblies, we can see it in the right bottom right. So in the 2 separate assemblies, the first one is the camera gyro and the second one is the data processor. So the stellar sensor uses an active pixel sensor in a wide field of view, miniature still camera and electromechanical system. So for the landing sensor, or last but not least, is the navigation Doppler lidar. And the 2 characteristics is it measures the velocity and range along 3 different laser beams and simultaneous line of straight measurements used to determine velocity vector and altitude relative to the ground. Those are our 3 parts of the sensors. Next slide, please. So I will walk you through the propulsion system in brief. So for the spacecraft guidance computer, for the central computing and the control, we have chosen the Chang's 3 space system, the X-band transponder system, we can see in the right side, the black figure. And for the attitude control thrusters, we based on the Apollo 11's RCS system using the R4D engine from Aerojet Rocketdyne, and you can see all the specs in the down, engine specs from thrust and the specific impulse, chamber pressure, dry mass, length, diameter, engine cycle, which will be pressure fed, and the fuel. We have chosen to use nitrogen, tetroxide, and hydrazine. And we will require these RCS thrusters to stabilize the spacecraft. We have a soft and rigid spacecraft stabilization system, while the main engine is running. The second stabilization system is in operation. Both engines got enough thrust, and during the docking at the station, when the main engine is off, the second engine will be running, which allows to position and stabilization of our spacecraft in the space more accurately. Next slide, and thank you.
Our landing gear is attached on 3 points with the main part. All these attachment points on the foot is articulated so that we can land on all kinds of surfaces. The 2 side rods have a fixed length. The longer one works as an hydraulic piston. During the flight, oil will be pumped into the top chamber, and so the landing system will move to the side of the spacecraft. For the landing, oil will be pumped into the bottom chamber so that the legs are going to spread out to have a better stability on the floor. Next slide, please. To avoid the too big shock by the landing, we need to use damper. In order to absorb the shock, hydraulic and pneumatic damper are used. The pneumatic will reduce the impact and the hydraulic will reduce the vibrations. For the 2 slide rods, we build a pneumatic and hydraulic damper. For the main rod, the piston will be used as a hydraulic damper, as you can see on the drawing. By the landing, the right volume on each side is pumped in. Then the access to the pump is closed. So the oil has to go through the piece with a small hose, and because of the high viscosity, the shock will be absorbed. We also use a pneumatic damper on the main rod. Next slide.
My name is Pavel Poletaev. I'm from Bauman University. When choosing a power source, we had to solve a number of several problems. We needed a power supply system that would power both the lander and the crew cabin. Since our engine uses hydrogen and oxygen as fuel, we decided to take an electrochemical generator, it's also called a fuel cell photon, which runs on hydrogen and oxygen as our main engine. You can see some of its characteristics on the slide. One fuel cell photon produces from 5 to 27 kilowatts. In our case, it generates 10 kilowatts. Our calculations show that this will be enough for one flight without refueling. Approximate amount of required power you can see in the table at the bottom of the slide. We will also use lithium-ion batteries for emergency situations. Basically, the energy system will be located in the area between the fuel tanks. A bit about antennas. We use 4 S-band antennas for long-distance communication with the Earth, Moon, or ISS, 2 in each direction. We took 4 so that in case of failure, there was a replacement. Also, we use 3 VHF antennas for communications during docking and landing. Next slide, please.
My name is Priscilla Nizio, and I'm from the University of Houston. So our attachment system utilizes rails, pins, and a robot arm system such as the Canadarm. The Canadarm is a remote-controlled mechanical arm used on space shuttle orbiters to deploy, maneuver, and capture payloads, and it aligns our system to the correct location. Our version of such system can be seen in the top left figure. Once aligned, a movable platform consisting of reinforced rails, as seen in the middle picture, allows the system to slide onto the landing gear through rollers. There are holes through the length of the movable platform and landing gear where pins will slide in to lock the system into place, which can then be retracted to allow the system to slide out of the platform when needed. A front view of our movable platform onto the docked system can be seen in the top right with the location of the wheels shown. We chose this location to attempt to minimize loads and allow for a smooth docking. So in action, the procedure is the Canadarm attaches and aligns our system, the capsule drops and slides onto the platform, and pins lock into place, completing docking. We're then able to refuel, making it possible for us to have enough fuel for the rest of the mission. So the full system can be seen in the bottom right figure.
So maybe it ain't much, but it is our honest work. Thank you for your attention, and I am grateful for my participants for working on this project. And now I present the crew cabin team. Thank you.
Thank you, Maxim. Nice to meet you. My name is Veronica. I am a MSTU student too. So we are a crew cabin team. So before designing, we compared several variants of spacecraft types that are able to carry 6 crew members to lunar base. They are a module, which completes the flight mission from ISS to the moon, then back to the ISS eventually, the combination of re-entry capsule and module, and 1 re-entry capsule. We decided to choose the last variant in order to lighten our spacecraft. We suggested to use a removable thermal shield. There are 4 main types of descent capsule. The crew experiences minimal G-force when using capsule in the form of spaceplane. However, the vehicle has a large mass because of wings. Thus, we decided to use a vehicle lift and body class. This type of vehicle has also small G-force values during re-entry.
Hello, my name is Timur. I'm from BMS2. The descent cabin designed by us projected for a crew of 6 people. The mass including all the system is about 7 tons and possible of autonomous existence of 10 days. right? A variety of systems are required for the cabin to function properly, and their correct position is an important part of design. For example, they install UDMH storage tanks outside the sealed section of the crew cabin.
Hello, my name is Bao Zhou from Bauman University. Irina and I are focused on radiation and thermal shield. When the reentry capsule enters into Earth's atmosphere with high velocity, it causes very high levels of heating. This is the reason why we decided to use removable heat shield. Our heat shield is made by ablative material. After a brief analysis of the advantages and disadvantages of quartz and carbon fibers, we decided to use quartz fibers like reinforced material for ablative material. Given the material characteristics, an approximate thermal calculation was carried out to obtain the temperature distribution in the package. Having the temperature distribution along the wall of the capsule, the required thickness of the heat shield and thermal insulation of the ship are determined. All materials in turn also serve as radiation protection. The following photos are shown on the slide for clarity.
Hi, my name is Vadim. I'm from Bauman Moscow State University. Since the flight time of the spacecraft is quite short, it was decided to choose a life support system based on resource reserves because it is more profitable at short distances due to the large mass of regenerative system units. Oxygen and water are stored in tanks, from which they are supplied to the cabin by a dosing device. Carbon dioxide is removed from a compartment and remains in absorption cartridges. Ensuring the normal temperature and humidity of the atmosphere inside the capsule is provided by a heat exchanger desiccant. Next slide, please. This table shows the mass characteristics of each system and the volume it occupies in the space of the capsule compartment. The total mass of the entire life support system is approximately 910 kilograms, including the thermal control system.
This is Zhang Yue from Bauman University and Harbin Institute of Technology as well. My teammate Wang Zhenyu and I are in charge of the power supply of crew cabin. Main power supply is guaranteed by fuel element photon, which is installed on the platform. We transfer chemical energy to electricity by composing liquid hydrogen and oxygen. Maximum power of photon can reach 25 kilowatts. In circumstances of emergency situation, the power will be generated by energy backup, a group of 40 Li-ion batteries. In total, we obtain nominal power 11.8 kilowatts. Here, the right table shows the detailed consumption of every system on board.
The first part of our docking system we want to tell you about is the one that binds together the ISS and our crew cabin. We will use the International Docking System for that. This docking system is composed of two parts, the passive part, which is the one on the ISS, and the active part, which is the one on our crew cabin. The active part has two main systems, the soft capture system and the hard capture system. And here you can see that the docking system between ISS and crew cabin is on the rear side of our cabin.
Hello, my name's Lyle. I'm studying at Politecnico di Milano in Italy. Here you can see a couple of the different concepts we considered for the connection system between the cabin and the platform. In the top right, you can see an axial connection method, which is what we considered first, and for us at least was conceptually simpler, but that created some center of mass problems and stability issues when the systems landed on the moon. So as my colleagues mentioned before, we adopted the horizontally mounted system that you can see in the left. The connection will be facilitated by the Canadarm2 on the ISS, So as you can see in the bottom right, we'll have the grappling attachment on the platform, while the cabin will remain docked to the ISS while they're coupled together. On the next slide, you can see, I guess, the evolution of the concept we had for the detachable connection between the cabin and the platform. So the basic concept is like a probe and drogue system with a bit, we wanted some, I guess, flexibility built into the system, because we're going to have a number of different attachment points over a span of many meters with thermal effects and things like that. So that's the kind of logic behind what you can see there. That's all from me.
On this slide, you can see general characteristics of design re-entry capsule. Thank you for your attention, and we'll introduce the orbital mechanic team. Thank you very much.
Hello everyone, my name's Chloe Tovar. I'm part of the orbital mechanics team, and I'm going to be helping my team present today with their PowerPoint. Can everyone see the screen?
Yes, screen is working, thank you.
Okay, awesome.
Hi everyone, my name is Zane. I'm a student at Brown University. Our team's task was to design a satellite constellation which would provide both communications and navigation on the lunar surface. And the reason why was presumably the control of vehicles from the ground would result in a signal delay and accordingly lower quality control. After determining the orbit life of our satellite, a system of orbits with the following parameters were chosen. As you can see, it's 2 orbital planes perpendicular to one another. And within each orbital plane are 2 elliptical orbits. Each orbit has 3 satellites, resulting in 12 overall. Can you go to the next slide, please? The most important characteristic of the proposed orbit system is its coverage of the lunar surface. And to estimate the satellite's motion, a simulation incorporating the influence of the Earth and the Sun without any corrective maneuvers was carried out. To better understand the results, the moon was divided into 3 regions of interest, as shown on the slide. In these areas, the period of complete coverage was determined. Most notably, the area adjacent to the base is completely covered for the satellite's life in the proposed orbits. Thank you.
All right, next slide. Hello, everybody. Adrian here, alumni from Rice University. So I'm going to be going over the transfer orbit trajectory from the Earth to the Moon. So what you're seeing here is 3 different reference frames of the same sample trajectory. So on the left, you have a 3D Earth-centered fixed inertial reference frame of the satellite going to the Moon. It seems to be lagging quite a bit, but you can kind of see some of the frames there. On the center, we have a 2D animation, and on the right, you can see it from the moon's, from a moon fixed reference frame. Next slide. So the majority of our work was done on figuring out these 4 delta V's. So again, we started from the ISS. And so what we need to do from there, the first step is to figure out our hyperbolic escape velocity vector. And so this is a 2D image, but the calculations, we started doing them in 2D just to get an approximation. And then we figured them out in 3D using MATLAB. And the method we used was the patched conic approximation. So as you know, Kepler's equations, they work pretty well for when you have just 2 bodies. But when you start to include the moon, then there's no analytic solution. There's no equation that tells you, how much delta V do you need to get to the moon? So there's different things that you can do, but one of the common ways when you're at the conceptual level is to do this thing called the patched conic approximation. And what that is essentially is you perform your calculations near the Earth, assuming that the Earth is the main gravitational influence. And then once you get close to the moon, you change all your calculations, assuming that the moon is now the majority influencer gravitationally. And the point at which you change from the Earth to the moon is defined by, if you see there on the bottom right, moon SOI. SOI stands for sphere of influence. So the calculations on the left, the first delta V from the ISS, that was all performed from the Earth reference frame. And then once you reach your escape velocity and you're on a hyperbolic trajectory to the moon, you intersect the sphere of influence, and then all the calculations on the right, 2, 3, and 4, were done assuming that the moon was the main gravitational influence. Obviously, there's still influence from the Earth, but that gets into more complicated modeling. So once we reach the sphere of influence of the moon, we're still on a hyperbolic trajectory, so we have to slow down, and that's the delta V number 2. So it's a combined delta V at that point, because we need to first go from a hyperbolic trajectory to a circular orbit, and we also need to change the inclination. The ISS is on an inclination of 51 degrees, and we wanted a polar orbit for this mission. So we do a combined delta V impulse to go from our hyperbolic trajectory at 51 degrees to a circular trajectory at roughly 90 degrees. Once we do that, we're still at a really high orbit, so then we have to lower our orbit. And so again, we do a third delta V that you can see there. And then once we get, and then it's elliptical at that point, so we want to circularize it at that lower orbit, and that's our fourth delta V. And then again, you can see, in 2 dimensions, I can't really show you the change in inclination, but the second delta V is both a circularization of the hyperbolic and a change in inclination. Next slide. And so here we just have some simulations of actually landing on the moon surface. So if you see on the top chart, this is a chart showing the velocity over time in seconds. And those drastic jumps in velocity, those are delta V's. And as you can tell, we're assuming that we're doing instantaneous delta V's. Obviously in real life, they would not be instantaneous, but for this stage of conceptual design, that's a fine assumption to make. On the bottom left, you can see the height over time going from an altitude of 200 kilometers. And then on the right, you can see our deflection. That's all. Thank you very much. Next slide.
Next slide. Hello, my name is Dinesh Mohamedova. I'm a BEM-STU student and transferring from Moon to Earth. For the return from the Moon, we have considered 2 cases. In the first one, we will use only engines. So delta V, there is some animation of our transfer, but can you please next slide so we can see pictures? Yeah, first delta V is necessary to put the spacecraft in a polar circular orbit around the Moon. Altitude of this orbit is about 200 kilometers. In order not to waste a lot of fuel on changing the inclination, we select the time of launching from the Moon and the time of entering to a transition orbit. It also allows us to get to the right point in orbit around the Earth and dock with the ISS. Using delta V bar, we transfer the vehicle to a transition orbit. Near the Earth, this orbit will have the parameters of the ISS orbit. Next slide, please. In second case, we consider it deceleration in the Earth's atmosphere. We will descend into the atmosphere at an altitude of about 45 kilometers above the ground. Then, using the effect of ricocheting, the capsule will rise to the altitude of the ISS orbit, while its speed will be 7.8 kilometers per second. This allows to put the station into the ISS orbit and dock it using a small delta V. In order that the overloads are not too large for tourists in capsule, it's necessary to slow down a bit capsule before entering. Also, for an emergency landing on the Earth, we can use the effect of ricocheting from the atmosphere to reduce the very high speed of the spacecraft and evenly distribute overloads during descent. And on the picture, you can see okay, it's a descent of our spacecraft. Orange line is surface of the Earth, green line is atmosphere, and blue line is trajectory of our spacecraft and trajectory of ISS. And that's all. Thank you for your attention. And if you have any questions, we'll be happy to answer them.
I've got a question for the team, if you're ready for just overall questions on the presentations.
Yeah.
Yes, of course, please, your questions.
So you have what appears to be 5 different groups working on a common approach to exploring the moon. How did you figure out when one particular group changed something in their design? How did you understand what the effect would be on the other teams? How did you do that?
I can answer this question. So we were working closely with a crew model team because their model was connected to our landing platform. And we had a lot of changes. Like from the beginning, we want to connect their crew model in a vertical position, but later we decided to make a horizontal position. So like the first, I think 4 days, we were changing our design, and then we came up with conclusion.
Did your changes affect the orbital mechanics or the capability to launch capsules and materials to the moon?
We were trying to make them the same.
That's kind of what I'm getting at, is in real life, there's always going to be interaction between changes that are good for you, but they may be bad for somebody else. This is one of the big problems in doing a large program.
Yeah, for sure.
About halfway through, we had a large meeting that pretty much went over of, hey, this is where we're at, this is what we're making, make our adjustments, and so we're all on the same page.
Did that happen once, or did you have to do that multiple times?
We did it several times with individual teams, but with all the teams, it was only the one time.
Okay. Another question that I have, I thought the presentations were excellent. One thing that I noted was among the 5 different groups, people used the word system probably 30 or 40 different times for different things. was there any thought about having the definition of what a communication system for the crew vehicle be kind of the same type of requirement for people on the lunar base, what their communication system would do for them? In other words, trying to use a common understanding of how all the elements of building this system on the moon would, a system to the people in the crew module has to mean the same thing for people outside who have to communicate with that crew system, that crew module. So, it applies to electricity, to power, to communications, to life support, all those aspects of what you're doing. Consistency is a really good thing in terms of how you define what the system is going to do. How did you guys tackle that?
When talking within our meetings, we didn't use so much nomenclature as description of what we were talking of our individual parts. So we didn't when we're talking to each other, we didn't continuously call it the system. We called it, hey, it's the small robot that goes and collects up resources. Hey, it's the thing that tells us to go get the oxygen.
Okay, last question, then I'll give the mic to somebody else. But in terms of what one team had to do that affected another team, let's say you're in the landing module and you have to get electric power from the power production people on the moon base. Was there any kind of description that says, I'm running the power station on the moon and I'm going to give the lander people 7 kilowatts, no more, no less? Did you have any description like that that spelled out what all these different elements were going to exchange?
Well, actually, I should probably step in. I'm not sure whether you can hear me clearly. I had some issues with internet connection today. Can you hear me clearly?
Yes.
Yep.
All right, thank you. Well, we actually had this kind of discussion with the team that was creating crew cabin. Since our energy system is self-sufficient, we are using hydrogen oxygen fuel cell. So we just needed from the base team to provide us with those two elements, and that was it. But we had several arguments about how much energy we can actually provide to the crew cabin, and they were asking for a lot. But fortunately, we found a solution which was that photon fuel cell was more than enough to provide us with sufficient power to power both their systems and ours.
What I'm getting at is if you can get agreement early on what the power that you're going to provide or you're going to get is, so it saves trouble later because you don't have to change anything. And legislating or specifying these exchanges early is a key part of how to do this.
Each team has their own team leader, and the team leaders communicate 24 hours per day.
Yeah.
Yeah, and the team leader of the crew team was actually communicating with the entire landing platform team pretty much the whole time.
Did you write any of this down?
Yes, of course. We were continuously making our own calculations to make sure that everything will fit.
Yeah,
And
but
plus,
beyond that, you have to have some agreement from one team to the other what you have discussed.
well, that was the job of team leaders.
Yeah, but did he write it down? That's my question.
I'm not sure whether he did. But probably, I mean, he had to, otherwise we wouldn't make it.
Yeah, I'm replaying to you a lot of the process that was used on the space station to coordinate Russia, the United States, the Europeans, the Canadians, Japanese, everybody else. These aspects of how you build your design have to be documented early. Otherwise, people feel like they have the freedom to do something else, and it may be quite disruptive.
We
I'm sorry,
gave this freedom
can
to the crew cabin because they were our cargo, so we said them like, tell us what you need, we will provide it.
I'm sorry, can I interrupt for your question about did we record any of our meetings, meetings of team leaders? And yes, we actually recorded them on the cloud, so we can share for our teams, for our different team leaders, to have our meetings, to have an access to our meeting, all of our meetings. So this is, I think this is the answer you wanted to hear. And actually we did.
Yeah, I just wanted to emphasize the importance of having these technical descriptions defined as early as possible.
Well, I couldn't agree more, but it was a continuous process. Like we had the first rough approximation, and as we went through each new iteration of our designs, we are getting more precise numbers, and eventually we've met somewhere in between.
More questions, if I might. I mean, I'm happy to leave the mic open to anybody else for a minute. I've got a couple more questions, though. Okay, so it would seem to me, I have not studied the lunar problem much, but it would seem to me as though going underground on the lunar surface might be a good thing to do. Did you guys look at that, or any type of robotic machine that can make a tunnel all by itself?
The problem of digging on the moon is actually quite complicated because the gravitational force is relatively low compared to the Mars and obviously compared to the Earth. Some digging mechanics that rely on the weight of a machine, the weight of equipment that we use for digging is neglected there. So we have to settle for some else means of digging, for example, some kind of explosions or something like this. And sometimes it gets a little bit tiring and you have to provide a lot of additional materials.
Last question I have on the power for the lunar base. 100 kilowatts seem to be your production figure, and that seems like a low amount of power to me.
So it kind of is, but only because we're considering the stages where we don't do any manufacturing yet. Of course, manufacturing takes a lot more power because it's digging, it's processing, it's using something else. But for base functioning, for its basic necessities, for the greenhouses functioning, it is enough. So it is an early concept, and later we can always try to extend our power grid by bringing heavier assemblies of nuclear reactors, or we can try to use to go more into the solar power, but solar power has its own limitations on the south pole of the moon because of the dust, because of the geographic location. So we have some problems with the expanding through the solar panels, so we have to settle for nuclear energy and bring bigger assemblies to make additional energy for manufacturing.
That's all I've got. Thank you.
Thank you for your questions. Does anyone else have a question for our teams, for our projects? Don't be hesitate.
Могу я задать пару вопросов?
Of course.
По-русски или обязательно по-английски?
Мы можем перевести вас.
Спасибо большое. Насколько я понял, вы собираетесь лететь на Луну, используя орбитальную станцию, то есть сначала с Земли на станцию, со станции на Луну и обратно, точно так же. А не можете объяснить цель этой остановки по дороге на Луну и по возвращению с Луны?
As far as I could understand, you are going to fly to the moon via a space station on the Earth orbit. So from the Earth to the station and then to the moon and then back from the moon via the station back to the Earth. Can you please explain on the reasons to use this kind of transportation technique?
Здравствуйте, мое имя Максим Ваюты, я студент МГТУ имени Баумана. Это, ну, по крайней мере, полет с Земли на Луну. Промежуточной станцией был выбрана МКС, то есть целью, что для полета на Луну у нас требуется очень много топлива. И если мы будем всю массу выводить сразу с Земли, то у нас будет перерасход.
Ну, понятно, то есть дозаправка на Луну, а при возвращении с Луны?
Про возвращение у нас была выбрана промежуточная станция МКС, чтобы... Ну, во-первых, потому что мы, как уже было сказано, уже тормозимся об атмосферу, и МКС был, потому что у нас достаточно большая скорость, и мы когда отскакиваем от атмосферы, как раз-таки выходим на орбиту МКС, и там можно пристыковаться, и потом уже спокойнее и безопаснее приземлиться.
Извините, не совсем правильно просто говорит, так что можно, наверное, даже... Мы не планируем приземляться на Землю ведь.
Well, the answer was given by Maxim Vayuta, Bauman, Moscow State Technical University. If you launch from the Earth directly to the moon, the mass of our payloads will require quite a lot of propellant. So having docked to the station, we can refuel, and Mr. Skripachka reacted that he understood the question. For the way back, the answer was given that we returned from the moon with quite a large velocity, and having first damped our velocity with the atmosphere, we enter the orbit around the moon, and then we can dock to the station and then relatively safely return to the Earth. The follow-up was given by Nash, which is we don't really have much a plan to return back to the Earth, so we'll use the station on the in Earth orbit as a base.
Также можно дополнить, что наша капсула, которая курсирует МКС Луна МКС, она является многоразовой, и изначально на нем нет типового щита, то есть она курсирует туда-сюда. При какой-то нештатной ситуации или при необходимости спуститься на Землю, мы на Луне крепим этот щит и, соответственно, можем приземлиться.
So I would like to clarify that our crew transfer vehicle initially doesn't have a heat shield to return back to the Earth. So we fly from the station to the moon and back. And if we develop some kind of situation when we've got to go back to the Earth, we install that heat shield while we are on the moon.
И платформа также является многоразовой.
And the platform is reusable. Thank you very much. Understood.
Но, насколько я понимаю, в этом случае капсула должна быть рассчитана на нагрузки при возвращении на Землю. Правильно понял?
And do I understand it correctly that in this case the capsule has got to be designed to endure the re-entry load?
Да, верно. Она рассчитывалась на вхождение в атмосферу.
Yes, that's absolutely correct, and we did calculate it for the re-entry.
В этом случае получается, что вы должны будете разгонять на траекторию к Луне, сажать на Луну, потом поднимать с Луны и возвращать обратно к Земле избыточную массу, то есть избыточную, поскольку избыточная масса конструкции, которая для Луны просто не нужна.
So that makes your structure quite heavy, and you have to accelerate to the moon and then back to the Earth. Quite a lot of extra mass, which is not really required for the mission.
Изначально на нашей капсуле на нем нет типового щита и нету этих как бы излишней нагрузки, ее нет. И щит наш является усиленным, и при входе в атмосферу он берет на себя, соответственно, основную нагрузку. Также мы облегчаем капсулу, используя разные типы кресел. Как известно, кресла при входе в атмосферу должны иметь определенный наклон и взводиться, и иметь демпфирующую систему. При полете МКС Луна, МКС, этих кресел, соответственно, не будет. Но они будут упрощенные.
So we try to optimize the mass of the crew transfer vehicle by assigning some load-bearing functions to the heat shield, which is reinforced. And we are also optimizing the mass by means of using various different seats for the transfer missions and for the return missions.
Понятно. То есть вы пытаетесь обойтись одним кораблем на все случаи жизни. А вы не пробовали разделить? То есть как бы один корабль для доставки на Луну, а другой корабль для возвращения на Землю в случае необходимости?
Ну, мы рассматривали.
I understand the purpose. You are trying to use the same vehicle for both missions, for the transfer to the moon and for the return back to the Earth. But did you have a look into the options when you use two different vehicles for those purposes?
Да, действительно, мы рассматривали такую возможность, но как бы будет затруднена отработка всех этих капсул, двух конструкций. Не проще ли просто использовать одну тогда?
We looked into that option, but it appears that designing and validating two designs instead of one will be more difficult.
Ну, вопрос спорный, конечно. Ну, спасибо.
It's kind of controversial, but thank you anyway.
Вам спасибо за интересный вопрос.
Thank you very much for an interesting question.
Можно несколько вопросов задать? Вопрос можно задать?
May I ask a question?
Пожалуйста. Скажите, пожалуйста, вот вы представили достаточно подробный проект функционирования базы на Луне. А не оценивали ли вы, сколько носителей, сколько, значит, кораблей потребуется для того, чтобы вывести оборудование, необходимое для размещения такой базы на лунной поверхности?
So you have presented quite a detailed project of the lunar base. Did you assess how many launch vehicles will be required to implement this kind of project, to deliver all that equipment to the moon?
Да, оценка производилась, когда мы рассматривали прежде всего стадии расширения базы. То есть мы рассматривали, что необходимо доставить, чтобы обеспечить какую-то возможную минимальную установку. То есть, но число запусков, конечно, выбрано достаточно грубо, потому что сама по себе оценка очень плавающая. Но у нас получалось, по крайней мере, для третьего этапа, вот такого базового, порядка 20-30 запусков от платформы. При этом большая часть из них, скорее всего, возвратные. То есть, что платформа имеет возможность вернуться, если она заполнена не на максимальную полезную нагрузку.
So yes, we did make this kind of assessment, and for the minimum configuration of the base, of course, this estimate is kind of rough. For the phase 3, we would probably need 20 to 30 missions of the landing platform.
Понятно, спасибо. А, значит, соответствующие алгоритм доставки этого оборудования такой же, то есть, соответственно, вы на МКС отправляете, а потом, значит, к лунной поверхности, оттуда приземляете соответствующее оборудование, аппарат. Как вы планируете доставку?
How do you plan to deliver all that equipment? Are you using the same transportation technique, first delivering it to the space station and then delivering it to the moon, or somehow else?
Ну, на самом деле, большая часть модулей, ну, почти все базовые модули, даже, наверное, все базовые модули проектировались таким образом, чтобы входить и по массе, и по габаритам в стандартную схему запуска. То есть, да, каких-либо сильных изменений под это не требовалось. То есть мы, наоборот, старались перейти в более стандартный режим, потому что было требование использовать платформу как основной метод доставки. Соответственно, этим мы и пользовались при проектировании.
So most of the base modules were designed to support that basic techniques, and we were based upon the requirement to use the landing platform to the maximum.
Хорошо, спасибо. И еще один последний вопрос. Все-таки посадочный аппарат, вы провели несколько различных схем спускаемого аппарата в виде капсулы, в виде, значит, челнока, в виде, соответственно, какого-то крылатого аппарата. На какой схеме вы остановились? Может быть, я пропустил этот момент?
Well, my third question would be, maybe I've missed it, but it sounded to me that you looked into various options of the Earth return vehicle, being a capsule, lifting body, or some kind of wing vehicle. What kind of option did you finally pick?
Мы остановились на классе несущий корпус, потому что брать аппараты типа шаттла и бурана, у них очень много будут весить конструкция крыльев. Поэтому мы решили их убрать.
We picked a lifting body concept because the wing vehicles will have too much extra mass, which is required by implementing the wings on the vehicle. So we decided to get rid of the wings.
Понятно, да. И торможение вы, значит, через атмосферу предполагаете, через вот такое вот отражение в атмосферу, да, я так понимаю?
Да, сначала...
Is my understanding correct that you are going to implement a dual-stage deceleration by the atmosphere, first submerging yourself into the atmosphere and leaping out?
Торможение об атмосферу мы рассматривали как запасной вариант. В основном будем тормозить двигателями, потому что это не нам... Торможение об атмосферу не дает такого выигрыша в топливе, чтобы использовать его как основной. Он рассматривался как запасной и как запасной вариант для экстренной посадки на Землю. В общем.
So we use that atmospheric braking as a backup option for the nominal return. We plan to use active braking by the propulsion system. For the reason that the dual-stage atmospheric entry is not that efficient from the propellant standpoint.
Я еще могу добавить, что другой причиной, почему это было выбрано в качестве дополнительного варианта, потому что при аэродинамическом торможении это может привести к дополнительной тепловой нагрузке на тепловой щит, и, соответственно, это будет увеличивать его толщину, и, соответственно, увеличится масса. И поэтому Поэтому аэродинамическое торможение все-таки рассматривается в качестве дополнительного варианта. Ну, еще, чтобы как раз выиграть по массе.
So I would like to add that we pick the active braking option because in case of using the atmospheric deceleration as a primary option, that would require the higher mass of the heat shield, which will lead to the certain consequences. So that's why we use the active braking as a primary option and the atmospheric deceleration as a secondary option.
Спасибо.
Thank you.
Можем тоже вопрос задать?
May I ask another question?
Пожалуйста, пожалуйста, please.
Ну, вопрос общего характера. Вы упомянули, что будет что-то типа теплицы, назовем это. А что вы там предполагаете выращивать?
So it's a kind of generic question. You mentioned something like a greenhouse on the lunar base. What in particular are you planning to grow in this greenhouse?
Мы рассматривали несколько возможных вариаций наборов полезных культур, которые позволяют обеспечить наибольшее соответствие калорийности. То есть по итогу у нас получился набор, состоящий, как мы провели наиболее эффективный в рамках площади и энергии набор, который состоит из риса, подсолнухов и там личинок шелкопряда, или схожий по структуре биоформ. Понятно, что это не самое приятное для проживания, поэтому любые другие модели, которые будут использовать более стандартные культуры, они занимают, конечно, больше места, но они при этом, скорее всего, и приятнее.
Well, we did look into several options in terms of I would put it, sets of organisms which would be cultivated in those greenhouses. And we addressed them based on the calorie output and nutritional value. And the final set we kind of converged to consists of rice, sunflower, and silkworm. This is not probably the most comfortable and most pleasant combination, but it serves its purpose, and then subsequently we can transition to the other kinds of organisms we would cultivate in the green.
Спасибо. Второй тоже вопрос такой. Вы сказали, что у вас там будет, как минимум один ядерный реактор, как источник энергии. Если что-то пойдет не так, варианты ликвидации последствий прорабатывались хотя бы, обсуждались?
So you mentioned that you'll use at least one nuclear reactor on the base as a part of the electric power system. Did you look into any kind of option how you deal with the consequences should any kind of accident takes place with it?
Отдельных вариантов ликвидации и локализации именно последствий не прорабатывалось, но изначально реакторы были отобраны и размещены таким образом, чтобы в случае их проблем воздействие на персонал базы было минимальным. То есть они были отнесены в отдельные кратеры, они там были погружены по большей части реголитом, чтобы предотвратить воздействие внешней радиации. И сами модели реакторов подобраны такие, которые имеют возможность регулировать свой отток энергии, соответственно, свое производство тепла в случае чего. То есть не работают по принципу рейтегов, а больше имеют
их можно заглушить в любой момент или что?
У них, да, они могут регулировать свой выход. То есть реакторы по типу Kilopower и, по крайней мере, точно Kilopower могут регулировать свой выход.
So we did not look specifically into the techniques of dealing with the consequences of the nuclear accidents on the moon, but we ensured our safety by picking the design of the reactor. So this is not a retake. This is we plan to use a real reactor. We can regulate the output of the power. So we believe it to be a safer option.
Спасибо. И если позволите, еще один вопрос специфический. У вас на схеме вот, перелетной между Землей и Луной коллега упомянул, что второй импульс, который с одной стороны переводит аппарат на селеноцентрическую орбиту, там же происходит коррекция наклонения. Как я понимаю, это происходит в переселении, хотя, в общем-то, плоскость выгодно поворачивать как можно дальше обычно от притягивающего центра. Или частично поворачивать в переселение, а потом уже основную часть наверху. Все-таки зачем в переселении плоскость поворачивать? Почему не как можно дальше?
Yeah, I had a look at your slide of the Earth to the Moon transfer, and at one point you perform a maneuver to tilt the orbital plane, and it appears that you are making that burn at periselenium, although an existing technique to do that actually involves the burn made after going through the periselenium to be as far from the center of attraction as it's possible. So why are you using this particular method?
I'm sorry, it was a little hard to hear. Which particular method?
Okay, I'll try to say it primarily. Your second impulse that is applied at the periselenium of your trajectory, you told that you will change the inclination with this second impulse. So it means that you change the inclination in the very proximity of the moon. Why not to change it somewhere in the apogee part?
Well, that's because, well, we started off, it was a hyperbolic trajectory, and then once we do the plane change and the circularization of that orbit, I mean, you're essentially, that's like the next opportunity to do your, like for your next burn opportunity, I guess. Like right after you're on your hyperbolic trajectory, we're doing the plane change at the furthest point from that we're doing from orbiting the moon.
Okay, but it's not the best way to change the plane. Okay, so just as a remark, I can advise both Russian and English-speaking participants. There are some articles of Gordienko and Ivashkin, I think available in English too, about such a free impulse desacceleration around close to the moon. So they were written in several years just before this workshop. So if you have a chance, you should read them, because they studied this question in very detail, and the problem can be optimized very dramatically if you correctly choose the points where you correct the orbital plane.
Okay. Yeah, thank you. Yeah, if anybody has that and you can link it, that'd be great. In the end,
I will type the last names of the authors in the chat.
Okay, thank you. In the end, it wasn't too bad of like the inclination change wasn't too much of a delta V hit, since we were already far away from the moon at that point. But yeah, I'm sure there's plenty to optimize with respect to the trajectory.
Hello, dear participants. Thank you for the presentation of your outstanding project. So really great job was done. I have just some small questions about the project. So the first one, as I understand correctly, you considered the collection of the regolith for the oxygen and water extraction on the daily basis. And so my question is, do you consider some reusing of the waters and oxygen? Because after several weeks of some extraction, I think you get some great amount of accumulated water in gases of basically redundant. So why not to reuse it actually?
Actually, the reusability was incorporated into the numbers. The problem is that we have to provide at the later stages all the lenders with the fuel for going back to the ISS, because this way they can carry much more of a payload. So that was the thing that was taken that much regolith to mine. So it's all basically going on a fuel.
Okay, got it. And the second question is about lunar dust. You are going to make a lot of operations on the moon surface, and it is known that the lunar dust is quite a dangerous and aggressive thing. And it is being held by some electromagnetic fields above the surface of the moon. So do you consider any means, any solutions to protect your equipment from this dust, from this problem?
We've considered some means of protection, but we haven't incorporated them in our concept. So we've done some research into them, but it's a relatively new problem, and all the equipment that is proposed is on the test stage. So that's why it's quite hard to make a meaningful decision about this.
Okay, thank you. So I don't have any more questions. Thank you for the project. It was really great.
Well, if there are no other questions, I can ask a couple questions. It's okay?
Yes, sure, Olga, please.
Well, one thing is following up on Dimitri's question about the greenhouse. Nutrition factors, of course, very important, but it has to be considered altogether, the selection of plants, because what you're going to do with the biomass it produces, and sunflowers are beautiful, but it's huge amount of the biomass it produces in there. So what you're going to do. And also, it will also require quite a lot of resources to grow it. That's another thing. So it's very important to look at the whole thing altogether as a system. We use the word system quite a lot. So did you think about biomass processing and that type of equipment in your greenhouses?
We, during the later stages of project, even at a much earlier stages, when the lander tried to use methane and liquid oxygen pair, we considered reprocessing biomass as the methane, but even though we had tried to reprocess all our unedible biomass to the methane, we still didn't get enough methane to fuel them up. So that's why we actually said them, like, we can't manage fueling you in a reasonable amount of time. So maybe you should switch to the hydrogen and the oxygens setup, because we can't manage to fuel you up. And there were a lot of issues like that. So yeah, we've considered repurposing the biomass, but with our need for methane gun, we haven't actually found time to repurpose it.
Yeah, the question was also about thinking it from the standpoint of plant selection.
Yes, so
actually have a plan for biomass, or like then that will be a problem. It won't be some source of additional resources. But okay, and I have another question also about your base. Maybe I missed it, but I didn't see any airlocks over there.
There are airlocks. They are separated.
I didn't see any.
They're quite small compared to the size of the base. So they are located between the inflatable, between those inflatable pods, those kind of small ones, because inflatable pods are relatively big compared to them.
Well, it's also how you deploy them too. So because those, and one last question, and again, I'm trying to be brief because it can be a big discussion. Of course, it's a huge project. It's amazing that you guys pull it together in such short period of time. So kudos to you. Thinking about the landing system, is it a universal landing system? So when you designed and we looked at all the elements that you bring to the surface, they all be easily integrated into that lander system? Because that's, I'm talking about mass and again, integration, so the sizes and,
So,
you know, together. And
yeah,
how
we've tried to consider for math and dimensions, actually. For all of our equipment, so starting at the nuclear reactors and ending with the all the airlocks, all the bridges, all the inflatable pods dimensions. But there was a slight problem because there is a problem with calculating the dynamics of an inflatable pod, because it's a very hard thing to hard to calculate and hard to look into in the just 12 days.
Okay, thank you.
Okay, may I ask a couple of questions?
Please, please. Victor, yes.
Okay, so being a scientific supervisor of the project carried out by the team lead on robotics, my first question would be to the robotics group. So how do you address the navigation and localization of the robots on the lunar surface? Excuse me?
Yeah, thank you for your question. Ismail said a few words about it during the presentation. Maybe I'll ask him to answer one more time.
So how do you localize your robot on the surface?
He might still be muted. Yeah, Ismail, you're still muted. We apologize. He was having trouble with that earlier today as well, getting unmuted.
Yeah.
Can you repeat the question, please?
Yeah. So how do you provide the capability for the navigation and localization of your robots on the lunar surface?
The system of navigation of the rover, it is possible to localize the rover who are at the proximity of the system. So it can work if you work on a little area without a GPS system, but it won't replace completely a complete system of navigation. Another problem of this type of navigation, it is there is not north on the moon. So you will need to calibrate, to define a virtual north by aligning the system of navigation on the stars. So you will need to establish some convention. And if you combine a star tracker with an inertial central, you can implement on the rover a complete system of navigation.
Okay, so you are using the system which is similar to the system used in aviation in past, like the local range navigation system, and you somehow adjust for the accuracy of positioning the beacon, right?
Yes, exactly. But I think it is important to adapt this system of navigation for use on the moon. For example, in aviation, the airplanes are in high altitude, but the rover will work on the surface of the moon. So we will have to change the form of antenna, adapt the range, etc. And if this system is implemented on a rover, maybe we don't want to spend too much energy in the communication system. So we will have to adapt all the system to a specific learner application.
Okay, thank you for the answer. And the second question would be more generic on the use of robotics. So did you assess the entire scope of operations on the lunar surface, and well, can you assess the percentage of operations done robotically or done by the crew during the extravehicular activities?
I'm sorry, I didn't understand the question.
So, well, if you take all the operations on the lunar surface, how much in percent is done by the robots and how much is done by humans?
I see robotics and electronics like a mechanical hand for human. With this type of matching, you can extend your capabilities. So, for example, during the Apollo mission, if they didn't have the rover, they could only run on 1 kilometer. But with the rover, they could travel on a distance of 35 kilometers maximum. So I don't believe in a complete autonomous system. I believe in an hybrid system where human can control the robot to perform some specific task. And I believe in a system where the human say a command like to the rover goes from the point A to the point B autonomously. So I don't believe in complete autonomous system and in very high-tech system, but more in a robust system and simple system where you can tell to the robot perform this task, perform this autonomously, etc. And like a real help for the human exploration.
Now, this is all true, but well, it's just been mentioned that the lunar base will have the airlocks, and that's the question, I believe, either to the team lead or maybe even to the general design folks. So there will be airlocks, so that means that the moon base crew would be able to get out of their crew modules, step on the lunar surface, wearing the EVA suit and do something useful on the surface. So my initial question was, so out of that entire scope of operations on the surface, how much is done by humans? And then like humans wearing EVA suits, what do they do and what do robots do on the surface?
I can't really answer to this question because it will depend on what human will perform on the moon. For example, maybe if a human will only stay in the central basis, they won't use a lot the rover. But if they go out every day to use the rover, so I don't have an answer to this. It will depend of mission planification and what will they decide to really perform.
Okay, but what do you do robotically on the surface? As far as I see, you actually load and unload the cargo from the lander, right? you collect the material, and what else do you do?
For me, there is two major possibility to use the rover on the Moon Explorer on the Moon. It is to carry a few passengers with their equipment, like the Apollo's rover. And the second use, it is to extract and carry some resources autonomously. And maybe another task we could have, and it will be the third, it is to have a rover like the Curiosity on Mars, which will explore autonomously the moon surface to find some new resource or to perform a cartography of the moon.
Okay, thank you. But it was mentioned on the chat that maybe the moon base team lead would step in and try to answer.
Yes.
Can I have a question?
Yes, please.
Sorry. Okay, guys. First of all, thank you very much for your brilliant presentation. Maybe I lost this topic. Did you maybe roughly calculate the budget of the project, or maybe annual spendings for the mission? I mean, from economical point of view. Thank you.
So I don't know if it applies for all the teams, but for our team personally, the proof of concepts and an assessment of some numbers, considering in-situ resource utilization, the base development, and something like this, was in priority over the economic effect. So we kind of considered the economical part of the question, but we haven't made any reasonable assessment about it. So.
How many launches you said spare to initiate the program? It's actually a very good assessment, because every launch, if you roughly, you know what your what kind of launch system you use, so that's kind of will give you a rough estimate of the cost. Of course, RD is on top of all of that too, so you need to develop all the systems. But every launch costs a lot of money. So if it's 25 launches, so it's quite a lot.
Okay, thank you so much. Я думаю, что нам уже по времени пора прекратить обсуждение. Вопросы очень интересные, и можно обсуждать его долго. Давайте оставим что-нибудь на следующий год при личной встрече. Мы всех приглашаем участников этого проекта, этой школы, поучаствовать в следующем году в очной школе, посмотреть друг на друга, выяснить невыясненные вопросы и продолжить работать вместе.
Well, I believe enough questions for now, because time is running up, and I think we've got to stop the discussion and leave something for the next year, because all the participants are absolutely welcome to come and see us in Moscow next year, so that we could get together, discuss what we didn't manage to discuss, and develop something new and do it face to face.
Уважаемые члены жюри, уважаемые гости, если кто-то хочет выступить, сказать что-то ребятам в назидание, пожалуйста.
Dear members of the panel, dear guests, if you want to say something to the participants, please take the floor.
Можно несколько слов?
Пожалуйста.
I would like to say something.
Уважаемые коллеги, ребята, Значит, вы сегодня представляли очень интересный проект. Этот проект у нас традиционно в университете проходил летом в очной форме. В этом году, конечно, ситуация не позволила нам всем вместе встретиться и пообщаться лично, обсудить нюансы этого проекта. Вот. Тем не менее, действительно, вы очень хорошо справились с поставленной задачей. В этом году многие вузы оказались перед лицом необходимости проведения дистанционного обучения. В частности, в МГТУ у нас соответствующее обучение прошло в дистанционном формате. Вот. Ну и ваш проект тоже показал, что мы готовы к тому, чтобы обсуждать эти важные аспекты будущей миссии на Луну в таком вот дистанционном формате. Значит, этот формат имеет и определенные преимущества, потому что, как вы видели, наши уважаемые гости сегодня подсоединились, астронавты НАСА, которые вряд ли приехали бы к нам, а у нас теперь появилась такая великолепная возможность с ними пообщаться. Вот. Ну и действительно, от имени руководства университета я еще раз вас поздравляю с завершением, успешным завершением этого проекта. Вот, и надеемся, что в будущем году мы с вами сможем встретиться уже в личном, непосредственно пообщаться на территории нашего университета. Вот. Это работа, которая ведется по пропаганде космоса, по соответствующим совместным исследованиям в области космических исследований, она очень важна. Она проводится уже очень давно. Ну, я сам в свое время был участником такого проекта еще в 1991 году, когда была соответствующая школа, Международный космический университет, который курировал Европейское космическое агентство. Вот, и наша еще во времена Советского Союза участвовали Московский авиационный институт, МГТУ. Вот, и ряд других вузов, приезжали иностранные участники из других стран. Ну, сейчас мы эту эстафету подхватили и проводим соответствующие школы у нас на территории МГТУ имени Баумана. Поэтому еще раз поздравляю вас, значит, и надеюсь, что те исследования, которые вы здесь проводили, они вам помогут в будущем, помогут в обучении в ваших высших учебных заведениях, помогут в вашей дальнейшей работе. И вот такие встречи, они помогают научиться работать в команде, работать в коллективе, потому что одному человеку, даже каком бы он одаренный и умный не был, какой бы у него не был хороший научный руководитель, не в состоянии соответствующий проект выполнить. Это может выполнить только такая группа, такой большой коллектив. Спасибо.
So thank you very much for the interesting presentation of an interesting project. Traditionally, we have it done face-to-face. So it was a little bit more difficult doing it remotely, but we still have done a great job. I should mention that most of the Russian schools face the necessity to convert their educational process to the online education due to the circumstances. So this format has got some strong points and weak points, and definitely the strong points are that today we were joined by the astronauts in this discussion who could not really come and meet us face to face before. So I believe that the activities to promote space development and space exploration are important, and this type of programs are important. So I participated in this kind of project myself in 1991. It was done by the International Space University under aegis of the European Space Agency and Moscow Aviation and Bauman Moscow State Technical Universities participated along with the other schools from various countries. So on behalf of the management of the university, I would like to congratulate you on the successful completion of the school program, and I hope that the experience and knowledge acquired will help you in your further educational process and your further job, because it doesn't matter how good your professors and scientific supervisors are, nothing is better than the experience of working on the project together with the other students, and only working in such large groups make it possible to resolve certain problems of the space exploration. So thank you very much for your participation. I wish you all the best. Thank you very much for coming, and thank you very much for participating in this project.
Спасибо.
Спасибо большое, Александр Юрьевич.
Thank you. Thank you, Alexander.
Олег Иванович, пожалуйста.
Спасибо большое. Я хотел поблагодарить ребят за интересный проект, за оригинальные идеи, и хотел бы пожелать им успехов в будущем, новой интересной работы и новых интересных идей. Я думаю, что у них все получится. И, конечно, отдельное спасибо организаторам. Да-да, перевод.
So thank you. I would like to thank the students for the interesting project and the interesting ideas. It was a pleasure to listen, and I would like to thank the organizers for the opportunity to participate.
Ну и, конечно, отдельная благодарность организаторам. Я думаю, что было нелегко организовать и работу всей летней школы онлайн, и этой встречи, этого обсуждения онлайн в том числе.
So my special thanks to the organizers, because I believe it was not easy to organize this summer state school in its online edition, and especially organize this kind of online discussion we had today.
Все, оно уже говорят напутственные слова.
В свою очередь мы хотим, Олег Иванович, сказать вам, что мы к вам приходили в ЦУП много раз, когда вы были на орбите, и общались с вами, вы отвечали на вопросы ребят. А теперь мы приглашаем вас к нам в МГТУ имени Баумана. Вы совсем недавно вернулись из своего 3-го полета. Бауманцы вас ждут. Мы с удовольствием, как только нас ситуация позволит нам в очном режиме уже работать и учиться, приглашаем вас в университет на встречу с ребятами.
All again, thank you for joining us today. We had several opportunities to come and talk to you while when you've been on board the space station during your missions, and you recently came back from your 3rd mission to space, and now we are inviting you to your home school, and Bauman teachers and Bauman students will be glad to see you and talk to you as soon as the situation resolves. So we invite you to come and visit Bauman.
Спасибо.
Спасибо за приглашение, буду ждать
Thank
встречи.
you very much. Thank you very much for the invitation. I will be looking forward to doing that.
Дорогие друзья, пожалуйста, может быть, американская делегация, мистер Эбби, пожалуйста.
So maybe the members of the U.S. delegation would like to say something.
С удовольствием. Это Билл Риди, летчик-космонавт США. Поздравляю. Отличная работа всех. 5 с плюсом. На Луну вместе.
So, hello everyone, this is Bill Reedy, the U.S. astronaut. Congratulations to everyone, great job done, together to the moon.
Спасибо, спасибо большое.
Thank you very much. Anybody else?
I'd like to
thank Victoria and the whole team for putting on an excellent workshop. And we appreciate very much having the opportunity to participate in the 25th anniversary of the workshop. It was put on under difficult conditions, but you've done an outstanding job, and I look forward to us resuming person-to-person contact next year, and look forward to another outstanding workshop. So thank you. Спасибо.
Спасибо. Спасибо большое.
Thank you.
Thank you so
Thank
much.
you, Mr. Reddy.
Может быть, кто-то из участников хочет сказать какие-либо слова своим друзьям.
So do the participants want to say something to their colleagues?
Thank you for all your work. It was a great experience, and we learned a lot and had a hell of a lot of fun. And hopefully next year we'll actually be able to come see you all.
Thank you.
Yes, thank you for putting on this great program, and I do look forward to hopefully getting to go and participate next year and explore some of the culture. Thank you.
Thank you from all of us here in the United States, and especially from the University of Houston. We really value this opportunity, especially being in Space City, and the opportunity to learn not only about our contribution to, to space flight, but also yours and all the other countries too. So thank you.
Thank you so much.
Я бы хотел всех участников поблагодарить и сказать, что на самом деле такой формат работы оказался сложным поначалу, но очень продуктивным в конце. И я думаю, что в целом эта программа может существовать в любых условиях, и в таком формате она даже будет, возможно, более продуктивной в научном плане, а не в общественном, для космической отрасли. Спасибо.
So I would like to thank all the participants, and I would like to say that initially this kind of format of working online seems to be difficult, but in the long run it proved to be more efficient. And I would say that it might be even more efficient from the scientific standpoint than the face-to-face one, when you prioritize the scientific exchange over cultural exchange. So, and I believe this way we can work on future projects as well. Thank you very much.
Спасибо, Максим.
Thank you.
I want to add something. That was my second time on SDTP, and it was my first time as a team leader, and I'm very thankful for my team. Thanks you guys. It was an honor to work with you. Everybody was working together, and that was a lot of fun here.
Ну что же, я передам слово Галине, которая все это время, все 10 дней держала ниточки в своих руках, осуществляла нашу связь. Пожалуйста, для торжественного момента предоставляется слово Галине сейчас.
At this point, I would like to give the floor to Galina Nisisheva, who's been a coordinator of this program for many days, who was actually keeping all the connections and arranging our meetings. So, Dalia, the floor is yours.
Thank you, Victoria. First of all, I'd like to say that it's not only me who work for everything to keep going and working. It's the hard work of everyone, every participant, our of course professor team, our organization team, our team leaders and participants. It's like joint work and joint
success, if I may say, because it is a success. We held our program without, okay, these slight problems, but everyone had fun, everyone had an experience, and I hope everyone will remember this school as great moments of their lives. And of course, for you to easily keep it in mind that you actually participated in our workshop, we will hand you the certificates that states that you were a participant of our summer workshop, the Space Development Theory in Practice. And the certificates will be handed to almost 70 participants, including our participants from Italy. It's Gabriele Reverberi from Genoa and Ismail Collin from Milan. Our participants from Bangladesh in the Shorfaras seed, our participants from Australia, Neil Thomas Campbell, our Harbin University colleagues from China, it's Ling and Jan Roos. Our, of course, the delegation from Switzerland, including Fabian, I'm sorry with the names if I am mistaken in any, Fabian Corit, David Forjon, Sejanova Miroslava, Mathilde Rossier, Gregory Toret, and Jamie Spinoza. Our team from Armenia, it's Diana Danilan and Vazgen Safarian. And of course, the team from United States, which are 15 of them. It's Zhena Shkar, Trey Bidi, Amanda Botti, Curtis Clark, Harry Espiloid, Dmitry Janopoulos, Janos Apollos, I'm sorry, Kelly Graham, Leanne Johnson, Priscilla Nisio, Colton Parkinson, Adrian Perez, Anna Sito, Chloe Tover, and Wendy Van. And of course, our Russian participants, and may I please ask Yelizaveta to show to us the certificates, how they look like, please. Елизавета, Лиза, пожалуйста, включи сертификаты. While she turning on the screen, I'll continue to list the participants. Our Russian teams includes Borzenkov Mark, Ilmaz Mikhail, Politaev Pavel, Vasily Fedor, Marat Ayarpetyan, who were team leader, Britov Andrei, Van Zhenyuy, Vayuta Maxim, Girin Ivan, Горбунова Кристина, Grigoryan Vadim, Denisov Mikhail, team leader, Жеребцова Екатерина, also team leader, Zakalushsky Alexander, team leader, Kamenev Nikita, team leader, Krapetyan Aida, Kasir Rikana Jorge Ruben, Kolchin Alexander, team leader, Kuznetsov Maxim, also team leader, Lamosh Patrick, Lysenko Maxim, team leader, Lyuba Mumi Timur, Muhamedova Inesh, Misisheva Galina, Nikonova Victoria, Anishuk Sergey, our participant from Omsk University, not from Bauman University, Pavlichenko Veronika, team leader, Porsiva Svetlana, team leader, Stogny Mikhail, Trinovsky Yana, team leader, Kukhlina Olga, Chan Yue, Shvetsova Arina, Shikерина Елизавета, Яковлева Анна и Yakubenko Yana. So this is our team, the whole team, and I wish you luck on your researches and scientific path. Thank you.
Ну что ж, спасибо большое.
Okay, thank you very much.
Команда, как видите, и ребята разных стран, разных континентов, но все мы были объединены в нашей школе. Спасибо. Я хочу поблагодарить также Галину Месищеву за то, что она сделала большую работу, Лизу Шикерину, Аиду, Поблагодарить Николая Павлова, ракета-модельный класс. Он состоялся, и Николай дал вам методические основы, как можно сделать свою первую ракету. Благодарю также Андрея Павлюченко за то, что он прекрасно провел вместе с Павловым экскурсию в лабораторию космической техники МГТУ имени Баумана. Благодарю всю нашу команду за то, что мы это сделали. И, конечно же, Виктора Зеленцова, который позволил нам говорить с вами и понимать друг друга.
Okay, I would like to thank the organizing committee, and I would like to thank Galina Mesisheva and Aida Karapetyan for their tremendous coordination effort. I would also like to thank Nikolai Pavlov for the rocket modeling class where he shared his mastership with us. Special thanks to Andrei Pavlyuchenko, who managed to pull together a tour of Orevo facility along with Nikolai Pavlov. And of course, I would like to thank Viktor Zelentsov for making it possible for us to communicate and understand each other.
Мне остается только сказать до следующего года, до 21-й школы, простите, до 26-й школы, и до новых встреч, нам хороших проектов, всем здоровья, конечно, в первую очередь, и хорошего состояния души, хорошего нам трудолюбия. Спасибо всем. Наша школа закрывается.
Thank everyone, and I would like to say see you next year at SDTP 2021, the 26th workshop of this summer school of this series, and I wish us all success and in our projects, let those projects be good and interesting. I wish everyone a success and good state of the mood. So see you next year, and at this point I would like to close the program of SDTP 2020.
Ваши сертификаты летят к вам.
And your certificates are flying to you.
Ну что, все, пока.
Okay.
Огромное спасибо. До свидания.
Thank you very much. Bye-bye.